Okay, so it's a pleasure for me to introduce Vadim Nikolayev. Do you write Vadim with I or Y?
Because actually, it's with Y.
Yes.
It's a Ukrainian transliteration, not Russian. But my first passport was issued by the Soviet Union, and it was Russian at the time. So I keep this as a pseudonym, you know.
Okay. Okay, so yes, indeed, Vadim started his career as a PhD student in Kiev, in Ukraine. And then he traveled a lot. He was involved in a lot of things. I've known him for a very long time. When I met Vadim, I think he was already working on contact lines and boiling, and we discussed that many times. He was a participant in a famous French group headed by Daniel Bessins on phase change applications, multi-phase flow applications with a strong connection to microgravity. But Vadim also worked on more non-microgravity phase change problems. And now Vadim is working at CEA in a collaboration with the group of Cassiano Tecchio, who is involved also in the PhD thesis of Alexandre. So it's a great pleasure to have him here today, talk about liquid film modeling.
Okay.
Vadim, you may start. Do you have a microphone?
Yes. Is it okay? Okay, great. Thank you. Thank you, Stefan, for this introduction. So I'm going to speak about the subject which is not that conventional. It's on the boundary between industry and physics. It concerns the pulsating heat pipes. So first I will explain what it is. Then I tell a little bit about the design of PHP, a method of this design, which is the only way of designing it. It's direct simulation, in fact. It's too complex. Then I will tell about some bottlenecks in the simulation models, which concerns the liquid film modeling. First, I will speak about the liquid film thickness modelings, and then liquid film length modeling, so involving the contact line dynamics. And here I will speak a little bit in more detail about the duetting at evaporation. And then I will conclude. Okay. So what is the pulsating heat pipe and heat pipe in general? It's a device that serves to transfer the heat from one point to another. You know, either to cool down the electronics or just recover the heat, whatever. So it's makes use of reversibility of latent heat exchange. So what happens is that you evaporate at one side, you accumulate the latent heat in the vapor, and then you transfer the vapor to the condenser part, you condense it, and you give back this latent heat, okay, basically. So heat pipe kinds differ by liquid transfer, because vapor is transported just by its expansion, right? But just when you generate more vapor, it proliferates easily. But the liquid is another story. You need to transport liquid to the evaporator part, and this is done in many cases by capillarity. For instance, in every mobile phone now there is a liquid which circulates, that cools down its processor, and it's the case of all the mobile phones now. And in every computer, in every heat, more or less powerful heat emitting device, there is a heat pipe now. So here you have for instance, the Hubble Space Telescope cooling system. So what is the pulsating heat pipe called in some parts of the world, in China and in the United States, oscillating heat pipes? Okay, but it's the same. It's a very simple structure. It's a meandering capillary channel, is a tube or engraved on a plate. It was invented, by the way, quite recently. with respect to other kinds of the heat pipes. So it's a meandering capillary tube. You put some fluid inside and they form plugs and liquid plugs and vapor bubbles inside, and when you apply difference of temperatures at condensate evaporator part, a miracle happens. The whole train of bubbles and plugs begin to oscillate spontaneously. Okay, so you see here an example of such an oscillation, and such device is very attractive for industrial applications because very simple, so reliable, light, and easily integrable because you can put it, configure it for any geometrical configuration, and in addition, it's extremely efficient. It can transfer kilowatts without any problems, just because fluid motion washes the dry areas once they are formed. Because the problem for capillary heat pipes, for instance, you have at some heat flux you have dry out of evaporator part, and it ceases to function. Here you have a motion of fluids, so it helps to increase these limits, heat flux, maximum heat flux limits. However, it involves multiple length scales. The channel length for this one, for instance, it's 50 grooves of 27 centimeters. It's about 14 meters. It's big length. And you see that there is some correlation of motion on this length. So you have a proliferation from some waves, pressure waves. So you have a kind of collective motion, which is a very interesting phenomenon to be studied by itself. Never mind. Never mind. It's wrong. I mean, well, at the time it was true, but it's a very old video. But I didn't find any better. So I will show later the same propagation of waves by simulation. So let's now go down to scale, to the millimeter scale, which is the scale of the Taylor bubbles inside the PHP. And when there is a motion of such bubbles squeezed in a channel, you have a deposition of a continuous liquid film on the walls of this channel, and the thickness of this film is given by the formula derived by Oscillating and Kéré. It's a very well-known correlation, which involves the capillary number related to the velocity of motion of the menisci, the deposit, actually, the film, the front menisci, which recede and deposit the film. Okay. The film characteristic film thickness is of tens of micrometers, and it is defined by meniscus velocity through this expression. However, the particularity of the pulsating heat pipe is that the film partially evaporates, thus in evaporator, thus creating the triple contact lines, and this is a single branch PHP experiment in which Etienne, I think, participated at the time. It was a internship of Lagubo okay, so it was 20 years ago, but since still it's very interesting visualization. So now I will tell a little bit about designing of PHP and the code we developed. So it's French, it's called CASCO. It's a French abbreviation for Advanced PHP Simulation Code. It's Code Avancé de Simulation de Caluduc Oscillant, which is a pulsating heat pipe in French. Why D? Because we need a tool to design the PHP, so it shouldn't last, the simulation shouldn't last for weeks, So it's a trade-off between code veracity and efficiency. But we can simulate only the bubbles of tube size. So the simulation procedure consists in breaking the virtual breaking of PHP loop, projecting it on a straight axis on which the evaporator, adiabatic, condenser zones are situated in a periodical fashion. So the problem arises how to model the menisci in 1D, okay? So what we do, actually, we replace the curved meniscus by flat interface with attached films. And when we simulate the bubble, we need to admit an arbitrary number of dry spots along it, because the bubble can be so long that it extends over several evaporator sections. Okay, so what about internal things to Casco? So it's limited to the plug-slug flow regime, so it's bubble plug, but in engineering we call it plug-slug. So we simulate the pulsating heat pipe as a set of oscillating, interacting pistons, and they're interacting through the elastic medium, which is in this kind compressible vapor. And it creates the elastic return force in this system, without which the oscillations is impossible. So the liquid plugs create the inertia and, of course, a viscous friction, which limits the oscillation amplitude. And the motor of oscillation is the phase change evaporator condensation, and mainly it occurs mainly through the liquid films deposited on the tube walls. Okay. In addition, we need to simulate the bubble and plug appearance and disappearance. It's bubble coalescence and bubble creation, basically by boiling. And we need to simulate also the heat diffusion in the PHP solid structure, which is an important point, and it takes a lot of simulation time, actually. Okay. The Cascade general structure begins with its initialization, okay? Then you progress in time and solve one time step for all these models I described, okay? However, there is a particularity in the system, because some plugs or bubbles may become negative, okay, numerically. So you need to cure. If you progress with such negative things, it becomes absurd and code collapses. So you need to actually to break from this loop, eliminate the bubbles and problematic bubbles or plugs, and return in the beginning of this time step. Yes. I mean, negative length or negative mass or whatever, you know. Negative temperature, well, something, you know, abnormal. Okay, so you need to cure this issue, and you return from the, you know, to the same departure point, and you redo this time step. And after this time step, you need again to check if everything is all right, and if other transformations of the system are needed, like adding of bubbles, for instance, if some conditions of local conditions of boiling are satisfied, okay? So then you save the PHP state if requested, and you return to back to perform the next time step. Okay, so for time marching, we use the fourth-order Runge-Kutta numerical method, which provides excellent numerical stability. The code is C++. It's object-oriented, so easy to modify. We need to perform the dynamic memory management, because the overall number of bubbles during the simulation can be really huge, so we cannot, you know, reserve the memory from the beginning for all of them. So the code now is error-free, no problems detected for years. And it provides a very good mass and energy conservation, so we don't need to, you know, reinitialize the mass by perturbing the system on the run. So I'd like to speak of the most important bottleneck in this code, which is the liquid film model. So the films are modeled of constant and imposed film thickness. We need to implement something really, you know, simple in this model. So we chose this way. So every film has a fixed thickness delta, and evaporation condensation mass flux is defined by the interfacial energy balance. It's a classical way of describing evaporation or condensation of the film. So the heat flux arriving from the wall is balanced by the latent heat generated at the liquid vapor interface, right? So another point is the film length. As the films are of constant thickness, we need to conserve the mass, right? So what we do is we provide such a velocity of the film edge, that is of contact line, to conserve the mass. So it's basically driven by condensation or evaporation. So you evaporate, you reduce the film length, you condense, you increase the film length, basically. So this method is certainly very efficient computationally, but in reality, the reality is very different. So first, the film thickness is not imposed, but defined by the receding meniscus speed. So we need to adjust somehow the thickness which we don't know, in fact, in the beginning. So what we do right now, we do a loop outside the casco, and we impose some thickness. We launch casco, determine the average plug speed from the simulation. Then we inject this plug speed into the formula here, and we calculate new thickness, and etc., until this procedure converges. So actually it's very quick. The convergence is extremely quick, so it's just few iterations are sufficient. So the main problem is that we assume the flow along the film, which is physically incorrect. Okay, because we, for instance, at evaporation, we reduce the film length, so we assume that this mass flows along the film. Okay, so it's absurd. In addition, the contact line dynamics is completely wrong. So we need to cure all those issues. However, the code works quite well. And it's, I just would like to speak about one application which we do in collaboration with Airbus Defence and Space. It's for cooling of power electronics of satellites. And this is not, of course, the industrial prototype. It's more testing test prototype. I don't have right to speak about the industrial things, obviously. So it's a 16-turn tubular PHP made of copper with 1 millimeter internal diameter. It has 2 aluminum spreader plates which serve as condenser and evaporator. You see here its size, and it's a subject of a postdoc of Slaven Bajic, ended just 3 months ago. Here is a CATSCO backend visualization of the PHP functioning. So the color code is blue, it's liquid plugs, and violet and gray it's vapor bubbles, and violet is liquid films. So you see the drying and this washing of dry spots by oscillating liquid plugs. And also you see those pressure waves that are propagating in the system, making this motion collective. Okay, so this is quite an efficient mode of functioning, but there are many others, of course. So actually what happens is that when you plot the thermal resistance of such a device with respect to the input power, you get this decreasing curve, which is characteristic for heat pipes. And these are experimental data, the symbols. And you have several simulation curves. And the parameter of this simulation curve is the what we call ONB threshold, or onset of nucleate boiling threshold, or you sometimes called nucleation barrier, which is actually the superheating of the tube needed to generate vapor bubbles. It's a very important parameter because boiling is extremely important in this system. Okay, So it's you see that the correspondence with the agreement with the experiment is provided for this value of 25 Kelvin, which corresponds actually to quite smooth internal surface, which is expected, you know, for this experiment. Okay, let's speak about the liquid film thickness study. Okay, and I will speak about the meniscus oscillation. So what we do, we try to calculate what happens in a tube when you, what happens with the liquid film attached to the meniscus when you oscillate the meniscus. Okay, when it goes back, it deposits the film. When it runs over the film, it absorbs the film. So it's a Brotherton-like problem for the film thickness. We solve it in the tube reference because of the oscillation, so unlike the Brotherton problem. So the contact line is pinned, so we do not consider what happens near the contact line right now in this part of our study. So the pressure is finite. There is no any problem of singularity at the contact line, and boundary conditions on the other side are introduced in some point which is quite high. I mean, the film is quite thick, so thickness much larger than film thickness, but much smaller than the other scale in this problem, which is the tube radius. Okay, so thanks to the scale separation, we can do such a hypothesis. So as the curvature saturates when you go further away, you know, from the contact line, so we have a parabolic solution in small slope approximation, which is a lubrication approximation used here. And it should match the meniscus shape, which is a spherical shape. So it's the profile is a circle of radius Rm that depends on the film thickness itself. So we need to solve this problem, and the result is here, and we compare it to the experiment which was done on just for liquid plug oscillation. Okay, so you just modulate the pressure from one end of the tube with some periodical, you know, pressure changes, and the pressure from the other side is fixed. It was done with a pentane in contact with its vapor. And you see the position of plugs. So there is one phase of the meniscus of the liquid receding, and it's on the stage you deposit the film, and the film has inhomogeneous in the space thickness just because the velocity of the plug changes in time, right? So it can be compared to this experiment where people measured actually locally the film thickness. And you see here the line, it corresponds to our simulation, and then the dots correspond to the experiment, and the crosses correspond to the actually Oscillating formula applied locally at each particular time. It's a quasi-stationary oscillation, which shows basically that there is no dynamic flow related to the meniscus motion. Okay, so at the advancing stage, there are capillary ripples which are formed close to advancing meniscus, which you studied a lot, I believe. So it's there is an agreement between simulation and experiment, and we were happy about this. So what you need to mention here is that if you have a look at the film thickness here, you see that the film doesn't change its shape throughout the oscillation. So in the middle part of the film, there is no flow. The flow exists only near the meniscus here, okay? And then in the middle of the film, no flow. So we can assume it to be quasi-stationary. So let's speak now what happens near the contact line. It's much more exciting. So actually, when you consider a film, you have a duetting phenomenon, which means here you see a duetting of a drop post just at the isothermal condition. When you put it on some surface, it begins to retract. And when it retracts, it forms actually a ridge, because the fluids that previously situated on the solid cannot flow inside the film because of strong hydrodynamic shear. So it forms a ridge, which is visible here at the edge of the film, and it's called the duetting ridge, or rim, or hump. Many people use different words for it. So, but it collects the liquid from the film previously situating on the solid. Okay. So what happens at evaporation now? So, of course, you have some evaporation from the flat part of the film. Okay, but you have a very strong evaporation here from the contact line region, because the thickness of the film is small here. So it should affect the duetting dynamics. So to find out what happens in this situation, we solve the again the lubrication problem, and we include here the evaporation heat flux and several other phenomena, which are first of all the Kelvin effect, which is the dependence of the saturation temperature and then of the evaporation flux on the local curvature. Okay, so the saturation temperature varies along the liquid vapor interface, thus creating Marangoni stresses, which is a term. The corresponding term is here, and you have also you need the relax, the contact line singularity. So you introduce the slip lengths, which via the Navier-Stokes conditions and via the Navier condition, and here the slip length LS that appears here, and what you introduce here is actually instead of describing a motion of the ridge, you move the substrate in the opposite direction, so that there's a term corresponding to this contact line motion. Okay. Yes. No, it corresponds to the temperature of the, well, actually, sorry, the answer is yes, because here in this particular problem we impose the homogeneous heating. So this superheating with respect to the saturation temperature corresponding to the pressure outside this film is homogeneous. But in this particular problem it's homogeneous, but in principle it can be inhomogeneous. Okay, so the liquid will have different temperatures at different points, because it follows actually the solid temperature. Okay, but in this particular problem the answer is yes. Okay. Okay, so to relax the contact line singularity, you have two effects. First, it's hydrodynamic slip, which is well known to relax the contact line singularity, which is the other effect is the Kelvin effect that relaxes it too. So you while the hydrodynamic slip proves to be more important in most cases, we keep the Kelvin effect because it makes the finite value of pressure at the contact line, which is very convenient for numerics. We do not consider the other side. We just impose the here the boundary conditions of infinitely flat film, because we know that what happens near the contact line is completely decoupled of what happens near the meniscus, because there is no flow in the film, in the middle part of the film, right? So the here we impose the flat film conditions. However, this flat film decreases in time, right? Its thickness decreases because of its evaporation. And there is some dry out time, which we call T dry. It's a time needed to completely dry out the film, but we never go actually to this time because in all practical situations its time is too big with respect to characteristic times. Okay, so we don't need to consider the film disappearance because of thinning. Okay, so at the contact line it's we impose the partial wetting condition, so we fix a slope by the value theta micro, which is provided by the substrate wettability. And we take advantage of the finiteness of liquid pressure ensured by the Kelvin effect. And the consequence of this finiteness is that the heat flux at the contact line is related entirely proportional to the contact line velocity. It's a formula that we derived. It's very convenient to use as a boundary condition, as a supplementary boundary condition, but it comes from the equation itself, so it's not really an external formula. So that's the result of this simulation realized for the refrigerant called FC72. And the initial thickness is 50 micrometers, and then the imposed microscopic contact angle is 5 degrees, and the superheating is 5 Kelvin. So it's what happens is that when you consider this problem is non-stationary in time, slightly non-stationary. The contact line speed slightly decreases in time, but this decrease is logarithmic actually. So you see it's weak variation, relatively weak variation. It's throughout of half of the drying time. So we can average actually this velocity and consider it as nearly constant. Okay. So what we will plot is our error bars. The top part corresponds to the 0,1 T dry time, and the lower part is 0,6. So you see that this error bar is quite short in all the cases with respect to the overall amplitude of the contact line velocity. So you see the second feature is that the contact line velocity increases with the superheating. It means that the dewetting is accelerated by evaporation. That's a very important fact, because this effect is extremely strong. Actually, in all practical situations that we meet, the film disappear not because they thin to zero, okay, but because they retract. Okay, so it's for instance the case of the micro layer in boiling, which is also a thin film. It disappears not because it depletes, as we say, thins, okay, to zero. It's because it shrinks. Okay, its length becomes zero. Okay. So, but as you may guess, to get such a simulation, you need a week of calculation. So it's not practical really to obtain such thing, and we want to have some more simple physical model. And for this, we need to make a multi-scale study, because there are multiple scales involved in such a phenomenon. And the smallest of these scales, it's a really vicinity of the contact line, which we call microregion. And it's in this microregion, what happens is that without evaporation, it's a liquid wedge. And with evaporation, this wedge becomes curved. Why? It's because you have very strong evaporation near the contact line, which causes the liquid inflow to the contact line. Okay, this effect is extremely strong on small scales. So you have a viscous pressure drop associated with it because of viscosity. Okay, so the pressure, say at the point A, should be larger than the point in the point B, while at the vapor side the pressures are nothing happens, so the pressures are the same. So the pressure jump that defines the curvature actually leads to the difference, inverse difference of curvatures. The curvature in the point B is larger than the curvature in the point A. It's very simple. It comes from the Laplace law. Okay, so immediately you see that the interface curvature increases near the contact line, which leads to such a bending of the interface, and a difference, big difference between the microscopic contact angle and the contact angle farther away. It's apparent contact angle, which we will not call apparent, but we'll call Voronov, because it's the angle which is not related to the contact line motion. It is the angle which is related only to the evaporation or condensation. Okay. So this is a problem widely discussed for complete wetting case, for instance, and most commonly it's attributed to the disjoining as an effect of disjoining pressure, which is not correct. It's an effect of viscosity. Okay, so it's whatever you use as the singularity relaxation mechanism, it will exist. Okay. Okay. So now we come to the multi-scale analysis of this equation, which is quite complex, has many terms, and we see here the interface slope variation along the bubble interface, along this wedge, and we see this effect graphically. So at very small, it's a semi-logarithmic scale, and at small scales you see that the angle corresponds to the microscopic, the slope corresponds to the microscopic contact angle, while farther away it saturates to this Voronov contact angle value. Okay. So if you now compare this with the numerical curve calculated for overall interface, you find out immediately that this microscopic scale provides a very good fit of the curve in this region, which means that all the for instance, that the flow due to the contact line motion is much smaller than the flow induced by evaporation and condensation, which can be proved, of course, by the scaling analysis. We did it in 2013. So it's also, of course, this is, so you can, in microregion, you can neglect safely this term, and the other term which describes the growth of the ridge. Of course, it's a much more macroscopic effect that you can ignore on such small nanometer scales. Next scale, it's a intermediate, what we call intermediate region, and on this region is the flow induced by the contact line motion primes over all the nanoscale effects that you can forget here, as well as still the effects created by the ridge growth. Okay, so it's a dynamic contact line problem that is well known in the literature, and it was solved in many papers. And first one is Voronov one, who derived this expression that gives you a slope as a function of a distance x, and what is you can make a fit of this curve with this law, which gives us this microscopic length, and because when x is equal to LV, then this term disappears, and the slope is equal to theta Voronov angle, right? And you find this LV is an intersection of the law of Cox-Voronov law and horizontal line corresponding to theta V. Okay, so in this case it's 20 nanometers. Okay, so which corresponds actually to the Voronov length induced by the slip length here, which is 10 nanometers. Chosen to be here 10 nanometers. Now we come to the macroscopic scale, which is a ridge, duetting ridge scale. And on this ridge, of course, the duetting ridge is circular because of the action of the surface tension. And if you plot this circle shape here, the slope in semi-log scale, you get a fit here. And if you do this matching, which was performed by Snoeger and Eggers in 2010, you get two such expressions. One of them resembles to the Cox-Voronov law, but actually it doesn't involve now the arbitrary slope, but the apparent contact angle visible on the scale of the ridge, right? and instead of macroscopic scale, you have this here, the ridge width. Okay, so you don't have unknowns in this formula. Everything is well defined, and the second formula, which is important as well, is the formula that gives you the receding of the contact line. We just need but to generalize this formula to the wetting case by introduction here of this volume of length instead of some particular case of slip length introduced by in the original work by Snoiger and Eggers. So actually we can use now it in evaporation case because this LV will depend on the evaporation rate, right? So let's create now a simple dewetting model by using it. It involves just these geometrical facts I mentioned previously, that you have all the liquid that previously covering the solid accumulates in the ridge, and by using these expressions, you actually come to four equations for four unknowns, for which are the ridge widths, the slope here at the ridge exit, the capillary number related to the contact line motion, and apparent contact angle. So you get all this data by knowing only the volume of contact angle. Only the input data to this model is the volume of contact angle, that is the apparent contact angle provided by evaporation in static case, which can be tabulated as a function of theta micro and superheating. And so it's takes now seconds instead of weeks to calculate, and you can get this contact line dynamics depending on the substrate superheating for any fluid. Okay, now you can plug in all these models into the PHP modeling. Okay, well, I don't have much time. We also validated it on the example of a single branch PHP, which is a capillary in the Durand geometry, which is put into the reservoir at constant pressure, and if you heat up its top, you cool down its middle part, and meniscus oscillates here, just like it oscillates in multi-branch PHP. That's what the experiment that Etienne participated. It's David Carré experiment. Oh, sorry. What happened? Okay. Yeah. So finally, you can verify those. Fortunately, I'm short of time to do it. It's okay. I can elongate a little bit. Okay, I will tell you then a little bit about this experiment. It's so here we used the Joule heating with transparent ITO films on both front and rear sapphire portholes. Actually, there were two windows, okay? And behind this transparent evaporator part of this part, we put a grid, wire grid, that gave us information about the shape actually of the liquid films. And in front here we have a sensor that provided us the film measurement by white light interferometry here. So the trick we did here is that we put a heating stronger at the rear porthole, you know, on the backside of the cell, film shape, and you see that the image of the grid is deformed, and this deformation actually allows us to calculate its shape, you know, because just by geometrical optics you can come from deformation to the actual from the grid deformation to the 3D shape of the film, which is like this. So you have these here, the dewetting ridges that, because you have receding of contact line from all the sides. What is important that you can calculate the apparent contact angle as a function of time, okay, here in this experiment. We relieve quite high values of apparent contact angles, which seem paradoxical because here it's ethanol on sapphire, which is at equilibrium, exhibits very small values. It's nearly wettable, it's very clean surfaces, so it spreads. So the contact angles are just of several degrees. But we relieve here quite high values of contact angle, quite fast receding of the contact lines. So we here is the time evolution of these ridges that you see, and what we can get from this experiment is the time evolution of the contact line velocity and the time evolution of the apparent contact angle, right? Unfortunately, we're unable to measure the local superheating in this problem because it's very tricky to measure everything at the same time. So, but from comparing the numerical curve I just spoke of the contact line receding and experimental decrease of the contact line velocity, we can recover the superheating as a function of time at the contact line, okay? By using it, then we can plug it into our theory and calculate the Voronov angle as a function of superheating, so we get a curve, okay? At the same time, we can apply this formula to get the same information from this formula, Cox-Voronov-like formula of Sneujder and Eggers, because we measure the apparent contact angle and we measure all those quantities, so we can recover the Voronov angle and we can plot on the same graph, okay? And we see a good agreement, so which gives us confidence we are having something real. Okay, so and then we construct with these findings we construct a new model for Casco, which is not yet implemented, but actually there is a difference with the old model, because here we do not impose the contact line thickness, but we calculate it, okay? It is still homogeneous in space because actually because of evaporation there is some slope of a film, because the film you deposit earlier, it has more time to evaporate, so it becomes a little bit thinner, so you have some slope. But the slope is extremely small. In the experiment I showed you, the slope was 0.01 degrees, so it's really very small. Okay, so then we need to model the dynamic wetting transition, because you need to find out when the film begins to be deposited on a solid, okay, at which conditions. So it's if the velocity of the meniscus is small enough, you have no film actually, and the apparent contact angle decreases with time. When you oscillate, you increase the contact line speed, the meniscus speed, which is the contact line speed, and at some point you have a transition when apparent contact angle reaches zero. It's a conventional model of dynamic wetting transition, which is now acceptable. So it's here it's a Cox-Voronov formula that more Sneujder and Eggers formula that gives us this decrease. At some point you go to zero and UCL drops to the dewetting velocity, because now you have a film and the contact line velocity is the velocity of dewetting. Okay, so it's completely different physics. So this is why you have a jump actually. So this, we just suppose that the velocity at which this jump occurs, it is scales like the wetting velocity, which comes from the simulations. The simulation result from this paper. There's not that much papers on the duetting transition. I would prefer that there were more.
We wrote one.
Ah, yeah, good. You will tell me about it. I will use it suddenly. So yeah, so it's you model it because the what you model, you need to model the film mass variation in time. So it consists of two components. It's increase because of film deposition, and decrease because of film evaporation, or increase of film condensation, whatever phase change. So it's when you deposit you have three situations. You can have a situation where there is no film, so the contact line and meniscus positions coincide. You have already a film, so this film will it's a situation of film collection when the meniscus goes over the film, so the film mass decreases, and you have film deposition when there is an increase of the film mass. So it's and you can apply such simple model to the single branch PHP, which is here. It was an experiment which was realized in Setil lab in Lyon. Here you have this PHP, and when you compare this is the experimental video, not very good quality, and this is variation of the meniscus height in time, and the advantage of a single branch PHP with respect to to its traditional multiple branch geometry is that you can measure in detail the positions, for instance, of the contact line, which is visible here. It's invisible in this video, but can be retraced from the detailed image analysis. So, you can measure also the pressure inside the vapor bubbles, which is very important. So you can compare it with the simulation, and you find a very good agreement, much better than the agreement with the basic model we proposed before. So this concludes my work. So PHP is a device promising for multiple industrial applications. It's not widely used because of absence of methods for its design, actually. Shows many interesting physical phenomena acting on length scales ranging from nano to meter scales. So 1D simulation remains to be most promising way of design of PHPs. And we proposed some studies. We did some studies around PHP to trying to justify and develop models for Casco code. And the duetting model is very interesting because it shows that the films usually vanish because they shrink, not because they thin. And this theory is applicable to many other systems as well, in particular to the microlayer beneath vapor bubbles and nucleate boiling. So I'd like just to acknowledge the contribution of my former PhD students, Xiaolong Zhang, Vladislav Janicek, Laura Fourgeau, and Mauro Abella, and postdocs, Jaroslav Nikrashevich and Slavin Bajic. And financial support of ESA, Airbus, and CNES. So with this, I thank you for your attention. This is a photo of Saclay, a very old one. You don't have newer. Nobody has, I think. Thank you very much.
Thank you very much for this interesting talk. Now it is open for questions. You? Wait for you for the mic.
Okay. Just can you check if it's turned on? Should be up. No. Okay.
for the talk. I have a question regarding the choice of the radius of the pipe. So if you do this on Earth, I understand that you choose the radius that is smaller than the capillary gravity length scale. But if you do this on space, what prevents the use of larger radius?
Okay, it's a good question. Actually, what we did, we tried to implement this idea. So we developed a pulsating heat pipe with big diameter tubes. Because nothing, a priori limits, prevents tubes from being capillaries in space. This doesn't work very well because the liquid flow becomes so fast that the surface tension is unable to keep the integrity of the menisci. You see, its Weber number becomes very high, and the menisci break down. So the flow pattern becomes completely messed up, and the PHP doesn't function as well. But it's preliminary, okay? Because we didn't actually see the experimental data in space. What we had, it's the experimental data during some parabolic flights, but it's tough. What we saw is a very fast motion, and Reynolds number, Weber number becomes larger, and which leads to this effect.
How do you initiate the system? Do you have like a long plug that eventually breaks into little, like as a succession of plugs and bubbles, or how do you?
Well, when you mean experimentally?
Yeah, experimentally.
Yeah,
Yeah.
you fill it up, okay? So you pump it out, okay? It becomes empty. You create vacuum inside, and then you connect your filling device. You open your tap, and then you let the fluid inside. So it actually forms long plugs.
Okay.
But at the first, when you heat it up,
it breaks into the smaller plug.
Yes, you have boiling, so it breaks into smaller plugs and starts functioning.
Okay.
I have a question regarding the assumption that the temperature profile in the films is stationary. Is that correct?
Yeah, across the films, we suppose the profile is linear. Yes.
And so the oscillating timescale or frequencies is 1 Hertz or so?
Well, it might be more than that.
Or even quicker. And the diffusive time across the film is also 1 second or maybe more than that. So how important is this?
It can be. It can affect the motion. So we can have some nonlinear distribution, some diffusion of temperature in the transverse direction in the films. Yes, that's true. Especially this is important for weakly conductive tubes like glass tubes. This is important. This was shown. But for metal tubes, this is rarely the case actually, because what happens is that you need to compare the effusivities of the media, that is of fluid and solid, and when the solid has a very high effusivity, usually it's very quick. The diffusion is. You can assume it's quick. So it depends on the plug velocity. So, for instance, if you have very quick functioning of PHP, this may be an issue. Yes.
And I had a question also about the shape of the PHP. So this single snake-like channel, is it done so because it's more efficient to have a single loop channel compared to several single straight channels?
Yes.
Independent. So how is the coupling between the various bubbles important?
Okay, I understand. So actually, from physical point of view, you have many different kinds of instabilities that appear, because in the single branch PHP you have only one instability that initiates the oscillations. Okay, it's related to the films, and okay, when you have U-type tube, okay, so you have two branches, it's already richer because you have an instability related to disbalance of pressures in different branches. And when increasing the number, you increase the number of degrees of liberty for such instabilities, and you lower the threshold for it's very difficult to start up the single branch PHP. You need a very big temperature difference, and for many multi-branch PHP, the threshold is really incomparably lower. So this is the reason.
Okay, thank you very much. It's fascinating for me because what you are talking about is exactly the kind of things we're studying in our group
so
now.
We'll discuss, yeah.
And I would not like to ask you a too technical question because maybe boring for the people who are not involved in the applied math of contact line and wetting, but I have a more fun question. There is an eminent colleague, Yuli Shikmurzaev, that says that everything that was done on the contact line by the people you cited is completely wrong, because on relatively moderate timescales, not infinitely fast timescales like you would expect on a nanoscale, but even on the millisecond scale, the surface tension is space and time dependent and so on. And so he has this interface renewal model. What do you think about that?
Well, I think that it's hard to believe. I mean, basically surface tension is a phenomenon that occurs on nanoscales. It's an interaction of molecules, molecular interactions, and admit that molecular interactions can lead to the relaxation time or such big macroscopic, I mean,
Milliseconds,
big
yes.
millisecond relaxation time. It's hard to believe. I mean, it's so difficult to prove or to be, completely countered. So, it's very hard because to realize such measurements, I don't know experiment that can formally prove or counter such ideas, but it's so hard to believe. I mean,
there was an experiment by Daniel Bonn a few years ago. Do you remember that story?
Well, yes, but
So
okay,
maybe we can discuss this later together.
yes,
Okay.
probably.
Thank you very much again.
Thank you for the invitation. It was an honor.